possibly from South America or on a Vega C rocket. That's still to be decided, but that's the preferred launcher. And this is a joint mission, just to make it clear, this is jointly funded by ESA and the Chinese Academy of Sciences. We've got 4 instruments on board. 2 of those are in situ, the LEA and the MAG instrument. They're measuring the particles in the magnetic field around the spacecraft. And then we have 2 images, and this is the real novel part of the SMILE mission. So we have the SXI, which is being built at Leicester, and the UVI. So the SXI is using those X-rays. And then the UVI is going to look down at the Northern Hemisphere auroral oval. And so the power here is the simultaneous measurements of cause and effect. We're seeing what happens with the solar wind coming in, and then what happens at the aurora, and seeing the whole chain of what's happening in that interaction. So we know we've got this situation here where we have the incoming solar wind, and certain conditions we can open up that magnetic field lines at the front of the Earth system. And this pressure, this magnetopause, is a boundary between our Earth and the solar wind. We want to see how that moves in and out. And this is important because this gives us a door to the ionosphere, what's the energy and the momentum that's coming down into our atmosphere. We don't know whether that process happens on a global sense in a fast way. So you can just see the sketch of a time series, whether this magnetopause jumps in, or whether it comes in very, very slowly, or whether it's stepped in some sort of stepped way of moving in and out as the conditions upstream change. And the SXI is that instrument that's going to do this. The SXI is based on, that means soft X-ray imager. It's based on technology that's been used for BEPI, for example, and other mission concepts and ideas here, space instrumentation. The inspiration for this camera is a lobster eye, which you can see on the top left. Now, if we zoom in on that lobster eye, you can see that there's very little pause. That allows the lobster to live and observe in a very low light environment. And in the X-ray sky, we don't get very many photons at all. So we need to be really efficient at collecting them. If we copy the lobster eye in the lab and we make a grid of these pores that are micron thick pores, we can do that in glass. We can make a very, very lightweight and cheap optic. So SXI is going to have a very wide field of view. It's a small telescope. It's not going to weigh very much, and that's beneficial to going into space, right? It makes it easy and cheap. You can see, we can have a look at it later, but there's a 3D model of the SXI down here that Matt and Cassie and Steve have helped me bring into the room here. So please come up at the end and have a look at it. This is our working model of the SXI, well, one of the models with 3D printed. So X-rays get focused by these micropore optics in a slightly different configuration than we're seeing here, but this was a BBC sketch that was made for a documentary, small documentary, and we can focus those X-rays and then image the magnetotube. This is the SXI model, the structural thermal model that went through tests at the Rutherford Appleton Laboratory in about May 2001. You can see it's being shaken on a vibration testing facility. So that was done just over a year and a half ago, and you can see the large white thing on the top is a baffle. That gets rid of any sunlight. We don't want stray sunlight coming in. This is a picture from one of the labs in the SRC, the old building on the other side of campus, whereby the model that was there was a couple of people in the room are up there. You can see the size of it relative to a person. So these are compact telescopes compared to XMM. XMM is huge. It's 7 meters long, whereas we've got something this size, which makes things much, much easier. And on the bottom image, you can see the micropore optics, or a couple of them, in the base plate where they're put and they're glued into place. We can't forget the other bits of the SMILE payload. So the top left-hand movie is showing a simulation of what we'll see in the Northern Hemisphere auroral oval. And you can see that auroral oval space changes. It's very dramatic on short minute timescales. The bottom left is the particle monitor, the LEA, and you can see the magnetometer deployment tests happening at ESTEC in the Netherlands. They use balloons to see this happening, and you can see that it should ping out in a minute, and all the engineers get very excited. That's happened, it worked, right? So that's good. So there's testing of various different components. And there's the SXI at the top that's incorporated onto the model of the whole payload all put together. So concentrating on the SXI, because that's where Leicester's got its main hardware interests, we're going to get one of these images. Now, I don't know about you, maybe if you're used to working with Hubble or JWST, you think, well, this is rubbish. But for an X-ray astronomer, this is pretty good, right? This is one of the simulated images made by Steve Sembe at the top there of what we'll see in the magnetosheath. Now, that's a 2D image, and we know this is a 3D structure. So we somehow have to go from this, without knowing anything else, to a 3D structure. So we need to think about how we're going to do that. And that's what a lot of the consortium is working on at the moment. So this is a worldwide consortium of scientists. So we have option one. We can use something that's used in medical imaging. You have your object in the middle, and then you take various different points of view around it, and then you build up an image of your object in the middle. Now, this assumes that that object's not going to move, it's not going to change. Otherwise, you're going to get a lot of blurring, a lot of error on that, which we could do under certain situations and with lots and lots of data. Or option two is we use a way of modeling. We use sort of forward modeling. We have our image, and we can use models. We tweak those models, and then we find the best fit model to the data. So eventually, we are trying to get to a point where, for certain solar wind conditions, which you can see on the bottom axis, we'll be able to get a good accuracy on the position of magnetopause. So eventually, we will be able to describe that magnetopause position, that boundary between the solar wind and the Earth field, using a couple of parameters, and that being 3D. And we're trying to do that in an integration time of the telescope of about 5 minutes under what we're calling moderate solar wind flux. If the flux of the solar wind is higher, then we might have very short integration times. If the solar wind is really weak, then we can then integrate those images for longer to make sure that we get the magnetopause to a reasonable degree of accuracy. So this reconnection process that we're trying to understand, and this is this door onto the ionosphere that's really exciting, linking up those two regimes. So we think about this using field line tracing. So you can just follow a field line through a model of the drawing of the field line and go from what's happening at the dayside back to the ionosphere. And maybe some of the undergraduates here have done a space plasma physics course with Steve Milan, for example, but you might have seen pictures like this, whereby we have ultraviolet auroral images, and you can see the auroral oval changing. And this, we know this causes changes at the ground with the green vectors here. These are from magnetometers, and they react strongly to what's going on up at the ionosphere. And then we can have an idea about what's going on, the competing processes in the whole system. We know, for example, that we've got reconnection happening here on the day side, and we know that the rates are not equal with what's going on the night side. But using these images that we're going to get from the ultraviolet imager, for example, then we can start to work out what's going on in that system. I'll just note that we haven't had images like this from the top left since 2005. So it's a big knowledge gap for humanity not to have these at all, right? But so SMILE's going to do great things. I hope I've convinced you. But SMILE has some limitations. I'm not dissing SMILE in any way at all, but we have to understand that there are limitations. SMILE is going to see these massive, large global scales of what's happening. But we really need to understand the response at small scales, medium scales. We need to understand what happens in the other hemisphere. We can only look at the Northern Hemisphere because the SMILE's orbit takes about 50 hours. And when we're going around the underside of the Earth on the south side, we have to turn off the instruments. We're going through the radiation belts, they have to be off for a few hours. And we don't actually get very much information about what's going on the night side. Tiny bit from the in situ, but we won't have any imaging there. So to do that, we have to use other instrumentation, other experiments around the globe to do that. That could be spacecraft, it could be ground-based. And the good thing about Leicester has this amazing heritage in both working in these space-based stuff and also ground-based radar, for example, in the Planetary Science Research Group. So we can do this. You can imagine an experiment where you're looking what goes on in the day side, and you can use a spacecraft that's on the same field line. You could use a radar looking up the same, and you can make comparisons about what's going on. And then, so what we're trying to do within the SMILE consortium, we're really trying to link up all these different types of experiments that we get across the globe. So you can see some images that have been taken from the SuperDARM radar. These measure how the ionosphere above us is being stirred, moved around. You've got radar such there in the snowy image, that's IceCat over on Svalbard, the Norwegian island. That makes very precise measurements of a localized region of the atmosphere. We'll also use cameras at the bottom left. That is a simulation of an all-sky imaging cameras from the ground over the North American sector. So if you stick a camera that's looking up and you link them all together with various cameras across North America and Canada, then you can get these wonderfully detailed images of the aurora, but taken from the ground up. And then we can compare that with what's happening from the UVI imager from SMILE. And then we can think about other spacecraft networks and link this all together. So this is one of my roles within the SMILE group is to lead a group of scientists to think about how we combine the data from all these, they're really varied data sets. They're different types, they're images, they're time series. They work on very different scales, both spatially and in time. So we need to think about how about we link the projects up together. And the good thing about what's going on in the community at the moment is that ESA and other big organizations are really thinking about this global holistic view of the system, and they're putting those words into documentation. So this is a report that came out that said that we really need to combine ground-based facilities with space-based efforts within ESA. So that was really positive to see SMILE mentioned in a recent document. And I've just been invited to talk to ESA. They want to up their game in terms of working with the ground-based community. And so various different projects, and I'm going to represent SMILE. We're going to talk about how best ESA can support missions that have a strong ground-based link up. So that's really exciting. So I will conclude and say that SMILE is going to revolutionize our understanding of what's going out in near-Earth space. We'll simultaneously image what we're going to see in the magnetosphere and the ionosphere, and answer questions about substorm storms, what's going on, this cycling effects of that dayside and nightside reconnection. But we have to really use all our expertise, whether that be in ground and in space. And stuff's ongoing here. So I have Matt, it appears in this image here. Matt is sat at the back in the blue top. He can wave to everybody. Matt is working hard on the electronics for the SMILE instrument, along with, I think that's Chris there. These are people that you might see walking around the department, and they're working really hard to make sure that all this instrumentation works and works really well. So hopefully, if for people already here, that will get to use this data in a couple of years to 2025. And if you're an undergraduate, then there'll be many opportunities for postgraduate and analysis in the next couple of years. So let me know if you want to come and join in with a SMILE Science. Thank you.